So our next speaker is Curtis Bright at the University of Windsor, and he will be telling us about a resolution of Lam's problem. Welcome, Curtis.
All right, thanks. And I'd like to thank everyone for coming, and especially the organizers for inviting me to give this talk on Lam's problem in our resolution using what's known as a SAT solver. So let's get into it. First of all, Lam's problem comes from a branch of mathematics called projective geometry. And so you might be wondering what's up with this image on the slide here, right? So this is actually demonstrating a principle of projective geometry. In particular, take a look at the train tracks. So we know in natural life, train tracks don't actually meet, right? Otherwise, trains would run off the rails. But if you look at what they look on when you project it onto a screen, it looks as if they do meet, right, at the horizon. And so this is actually a principle of projective geometry which you can formalize, and that any two lines in a projective geometry are going to meet somewhere. I'll come back to that, but I also wanted to talk about what a SAT solver is. So when I say SAT, I just mean satisfiability. So this is the classic problem from logic or computer science, where you're given a logical expression and you're asked, can you make this expression true, right? Can you find out some assignment of the variables which is going to make the expression true? And so we'll focus on the Boolean domain, so all the variables are either true or false. So in theory, this problem is finitely solvable, right? You could just try every possible assignment. In practice, there's way too many. However, and this is quite surprising, but SAT solvers are programs which will solve this problem, and they're actually very effective in many cases of interest. So for example, a hardware or software engineer, when they want to prove that a circuit is doing what it's supposed to, they'll actually go to the trouble of reducing that problem to Boolean logic, and then you run a SAT solver on it. That's actually the fastest known way to solve the problem. So it's kind of mind-boggling that Boolean logic is actually used for that. And another example of this is on the right here, I've given you a chessboard. All right, and then you replace a queen in every square, and you want to color the queens so that queens which are could attack each other are colored differently. Then the question is, how's the minimum number of colors to do that? And it turns out the answer is 9. So this is an optimization problem, right? And a SAT solver can solve this very quickly in a second, but it also does something more interesting. Not only does it give you the 9 coloring, it also gives you a certificate that there is no 8 coloring, right? And so this is interesting because if you were to write your own search for such a thing, maybe you could find the optimal coloring, but how do you prove to someone else that that coloring is optimal, right? With a SAT solver, you can give them a certificate which is then checkable. All right, the other software system that we use is known as CAS, or a computer algebra system. These are just systems that do mathematics, right? At a high level, you give them matrices or graphs or groups, and then you ask to do computations on these objects. For example, take this graph here, you can do compute the graph of symmetries, and then do computations in that group. All right, so the paradigm that I want to propose to you is basically SAT plus CAS. Use both of these systems in the ways that they're meant to be used, because note that SAT is really good at search, right? Because the SAT problem is inherently a search problem, whereas CAS is really good at mathematics, but not so good at doing search. So their strengths are complementary. And so my research program over the last several years has been to come up with ways to exploit the power of the search power of the SAT solver and the mathematical power of the CAS. And we've applied this system called MathCheck to many different types of combinatorial objects, from number theory, graph theory, and design theory. So here's one particularly nice looking one. This is actually a Hadamard matrix, or a cross-stitched version. So this is what happens when your partner is very artistically inclined. So the stitches here represent ones, and the lack of a stitch represents a -1. And then this is a Hadamard matrix, so any 2 rows in this matrix are orthogonal to each other. So that's a very restrictive condition. It's hard to find these matrices. I won't get into how we did it. You can check out the website if you're interested. And what I do want to talk about is projective geometry, as I alluded to. So I love this problem and branch because it goes back all the way back to the founder of geometry, right? The inventor of the axioms for geometry, Euclid. He did something interesting, right? He gave a small set of axioms which characterized all of geometry. And the interesting thing was all the axioms were very simple, except for one called the parallel postulate, which was more complicated. And so the natural thing to try to do would be to try to prove the parallel postulate in terms of the simpler axioms, right? And mathematicians tried to do this for 2,000 years, they failed consistently. And it was realized in the 1800s why they were failing. It's because this is an impossible task. The reason it's impossible is because there are models of geometry where the simple axioms of Euclid will be satisfied, but not the parallel postulate. As an example, the projective geometry that I alluded to, where any two lines are going to meet at a unique point. So there are no parallel lines whatsoever in a projective geometry. This is actually consistent. And in fact, once you know these things exist, the natural question is to try to classify such objects, right? At least could be classified the finite cases. So say there's only a finite number of points in your geometry. What do they look like, and what can you classify them? So mathematicians have studied this. They've solved the problem in dimensions 1 and 3 and greater. The only case which remains to be solved is exactly when there's 2 dimensions, right? This is known as a projective plane. So let me give you some examples of projective planes. So the axioms are actually quite simple. If I have them on the slide here, any two pair of lines meet at a unique point. Any pair of points define a unique line. There's an order condition saying every line contains the same number of points. All right, so quite quickly you can check that a triangle satisfies those axioms. It's the simplest possible case, right? Any two vertices define a line, any two lines define a vertex, and there's 2 points on every line. So the question is, can we go higher? Can we go to order 2? And indeed, it turns out you can, and here it is. And so take a look at it, and some of you might be thinking, okay, well, wait a minute. You're pulling our leg here, right? It's like, you said that there's a collection of lines, and then I see some lines in a circle, right? So what gives here? So in fact, it is a line, and you can verify for yourself it is a line by the definition of what a line is by these axioms, right? So if we consider lines being, 2 things which are going to meet at a unique point, this indeed is a line. You can check all the axioms for yourself. And in fact, we can actually go one greater. We can go to order 3, and here you go again. It gets harder to draw. There's 13 points, so 13 lines, 13 different colors. But you can check indeed all of the axioms are satisfied. So the question is, does this top out at some point? Maybe you can go on forever. Can you keep playing this game? In actual fact, up to 9 you can play the game, except at order 6. So what happens at order 6? This would be 43 points. You don't actually have to draw 43 points on a piece of paper and try to connect all these with lines. This would be a mess. In fact, there's an actual theoretical obstruction. There's a necessary condition that does not hold. You can prove this mathematically. So the order 6 case is eliminated. Other cases are eliminated as well, but not the order 10 case. This is a very, very interesting case because, first of all, no projective plane of order 10 is known, but there's no theoretical obstruction to such a plane existing. So you could conjecture either way. In the lack of an obstruction, maybe it actually does exist. We just haven't found it. So this is Lam's problem, right? Lam, it's named after the mathematician who studied it extensively in the 1980s for about a whole decade, and he was able to resolve it, as we will see. And he basically points out this is an infamous problem, even dating back. Here's Marshall Hall talking about it in 1955. He points out, okay, the 10 case is the critical case, the first open case, and he raises the possibility, okay, computers are starting to be developed. Lacking a proof either way, it's a natural thing to try to search for this thing, right? The question is, can we use computers to help resolve Lam's problem? So first of all, you need a way to encode the problem into a computational format. You're not actually going to use those nice colorful diagrams. What we're going to do is use an incidence matrix. This is a 0-1 matrix where the rows of the matrix represent the lines of the plane, and the columns of the matrix represent the points of the plane. Then you have a 1 in the ijth entry of your matrix if their ith line contains the jth point. So I've given you 3 examples here, and you can check again the axioms are satisfied. So in particular, the projective axiom, which says any 2 lines have define a unique point, is going to be their inner product is 1. So take a look at, say, the first 2 rows of this matrix. Their inner product is 1 because they share the second point and no other points. And you can check that for all pairwise inner products are 1. So in theory, you could just run a search for such matrices, but there's way too many of them. It's a non-starter. But this is where mathematicians have a lot of powerful theorems which allow you to structure the space. In particular, let me give you 2 quick definitions from coding theory. The first is that a code of a projective plane is going to be the row space of the instance matrix. modulo 2. So it's just a linear span of 0, 1 vectors, and you get a set of 0, 1 vectors. And then the weight of a 0, 1 vector is the number of ones it contains. All right, so it's just also known as the Hamming weight. It's a sum of the entries. All right, so the reason I give these definitions is because of this theoretical breakthrough of Asmus in 1970. He did something very interesting. He assumed the projective plane of order 10 existed, and then derived properties about it, the weight distribution of the code. Now, this is very interesting. So you don't even know, you don't have the matrix in your hand, but you're actually able to derive how many vectors of a given weight there should be. Well, in particular, you can derive there must exist a vector of weight 15, 16, or 19. This actually allows you to resolve the search because it splits up the search into 3 cases, 15, 16, and 19 code words. So many researchers search for these vectors. You can see them at the bottom there. And in the 1989, it was actually found, the search was complete and no code words of these weights were found. This is by Asmus's result of proof that Lam's problem is solved in the negative. There is no projective plane of order 10. You can see the running times here are quite extensive, especially in the higher weights. These running times were scaled to be on a VAX machine, which was a super mini machine of the era. You know, it was the size of cabinets, but it was very fast.
Why is there a relatively
Okay, so correctness, so this is actually a proof, right? There's an issue that authors were very upfront about, right? There may be possibility of error because this was custom written software that was only run a single time on a single piece of hardware. And worst of all, there was no certificates that were produced, right? At the end of the day, when the computer says search complete, how do you know the search was actually complete, right? Maybe there was a glitch, maybe the program was administered wrong. Something could have happened that there's nothing to check at the end of the day. And even worse, it was custom written software, right? So everyone who's written a program or used a program knows lots of programs have bugs. Even the most well-used programs have bugs. So it's almost a certainty there's some kind of bug. The question is, does it influence the final result or not? So in our verification, we actually found it did not. You know, we verified that there is no such plane. However, some of the intermediate results, there was discrepancies found. So some of these crucial numbers, you know, partial solutions, we should find the same number of them. We actually found differences between not only the original search, but an independent search, which itself found discrepancies. So this just goes to show you how hard it is to write custom written software to do searches. So coming back to non-existent certificates, we want to put things on a more sounder foundation here, right? And the idea is if we can use a stat solver, as I mentioned, you get a certificate at the end of the day, which can be checked by a third party. Once the third party believes in the encoding, then they can believe in the non-existence without trusting any search whatsoever. The idea is, how do you encode something into Boolean logic? Well, this is sometimes tricky. Boolean logic is very primitive, but there is a nice isomorphism between 0, 1 and true and false, right? The entries in your matrix are 0 and 1. The values in Boolean logic are true and false. So we just let 1 represent true, 0 represent false. So we just have a variable for every entry in the matrix. How do we go about encoding the projective axiom and these other axioms? So SAT people have worked on these sorts of encodings. One of the tricks is to make it as simple as possible, right? If you want to say every pair of lines meet exactly once, you can say they meet at most once and at least once, right? So we can go ahead and encode these in 2 different ways. Let me just show you what the incidence matrix looks like, first of all. So this is the incidence matrix or the start of it. So this is the first 45 rows. The gray entries are unknown. The black entries are known to be 1. And this is all on the assumption that a weight 15 code word exists. You make that assumption because you can prove the nice structure that is shown here. This was all done back in the 70s. You know, this is all mathematical. There's no searches involved. So the stat solver's task is then to try to fill in the gray entries. And so how do we do the encoding? So I take 2 random lines in that diagram, and let me show you how it works. So if we say that these lines meet at most once, take a look at the 2 highlighted entries there. If they're to meet at most once, both of those entries cannot be true. If both of those entries were true, the lines would meet twice. Their inner product would be at least 2. So they can't both be false. At least at least it can't both be true, at least one must be false. So what you can say is not A or not B, shown down at the bottom there. This is what's known as a clause. So this is what logicians like to the notation they like to use. And there'll be lots of clauses like this. I'm just showing you one of them. So this is the encoding for at most one. Then let's say we want to encode they meet at least once. So again, take the same two lines, but this time we want to look at these 6 entries. Now these entries cannot all be false. If they were all false, then the lines would not meet at all. Their inner product would be 0 by inspection. And so what you come up with is another clause. And again, you can give this to the SAT solver. There'll be lots of clauses which look like this. They form the encoding. So to give you a sense of the numbers here, if you just look at the first 27 rows of your matrix, you're getting a SAT instance with about 1,000 clauses, 150 variables, but 10 to the 18 solutions. So this is the problem with these searches, is that the search spaces are just enormous, right? You wouldn't want to try to enumerate all 10 to the 18. However, you can use some tricks that most of these solutions are actually the same. Because if you consider them as 0-1 matrices, and you allow yourself to permute the rows or columns freely, you can actually translate most of them into the same canonical form. So what you really have is about 1,021 different distinct equivalence classes there. So we definitely want to only limit the search to those 1,000 equivalence classes, but the question is, how do we do this? How do we come up with this isomorphism blocking, as we call it? So the idea at a high level is the SAT solver is going to be executing the search. It's going to be finding partial solutions, right? Partial projective planes. So here's an example, a 4.6-line partial projective plane. I give it to the CAS, and the CAS is going to analyze it. It's going to say, well, look at this. If I rotate that partial solution by 180 degrees, I get something which is the same. It looks the same, right? And therefore, I can block it, because anything which is extendable from the first is going to be extendable for the second. So I'm not losing anything by blocking the second partial solution, right? And the reason why this is so powerful is that you can do this for every single symmetry that you find, right? Every time you find a symmetry, you block another solution, and this is limiting the size of the search space. To give you a sense of some of the numbers here, in the weight 19 code word search, the problem here is that there's a huge number of ways just to even start filling in the matrix. In the weight 15 case, there was just one that I showed you. In the 19 case, there's about 56 million, but you can limit, a lot of those are actually the same up to symmetries, right? So we actually did this search in 2 ways. One was just using a pure SAT approach, using the kind of similar type of encoding. And the second was using SAT plus CAS, where you remove symmetries. And basically the upshot here is, not only is it faster to compute, it's also much fewer starting cases to start from, because you're not losing anything by only considering all the solutions in the second case, right? You don't actually have to consider all the 56 million. You can just get away with 650,000. And we did some double checking, which everything in the second was actually did generate all of the ones without the symmetry breaking. All right, so once you have all the starting structures, you can generate SAT instances for each of them, and you run the SAT solver, using state-of-the-art SAT tricks. You get back unsat for all your instances, which is then therefore a proof that the projective plane does not exist. Moreover, as I mentioned, you get the certificates, which you can give to a third party. They can verify, yes, all the instances themselves are unsatisfiable. Now, the certificates are actually quite large. They're about 110 terabytes, but they would fit on maybe not your home computer, but a computing cluster. In real time, it was less than a day of computing across 1,000 processors, but it was about 700 CPU hours to do this on the cluster we were using. This is actually the fastest known verification I'm aware of. Wah did one in about a decade ago in about 1,700 days. But of course, he was using his own code, so it's not directly comparable. Now, this is not necessarily the end of the line. There's still possibility of errors. So there's 3 main sources of trust that you need to believe there's a result. First of all, the SAT encoding, of course, has to be trusted. I gave you an overview of it. But also you have to trust the generation script for the SAT encoding, which is, you know, anytime, like I mentioned, anytime you write a program, there's a possibility of bugs. However, I would say it's much easier to write a generation script for those clauses than it is to try to write a search program, right? In the second case, you have to trust the proof verifier. This is a standard assumption because these are very well-tested pieces of software, and you know they have very small kernels that are you know, analyzed extensively. The third case is the isomorphism blocking clauses also have to be trusted. They were generated with a CAS library known as Naughty. So Naughty would be the most complicated code that we used, but we did do some double checking of those results, right? So when Naughty returns two things that are isomorphic, you actually get a labeling of that isomorphism that you can explicitly verify. Of course, then you have to trust our verification code, but it's going to say that we didn't just blindly trust Naughty. All right, so in conclusion, Lam's problem is a really great application of SAT and CAS techniques, but I want to stress just how applicable this is because there's lots of problems where you want fast, verifiable, and expressive searches. Right? And the SAT solver gives you fast and verifiable, the CAS gives you expressiveness. So yes, it does require possibly thinking about your problem in a different way. You have to, you know, SAT and CAS are both niche areas of computer science. But if you can do that, if you can encode your problem into Boolean logic and possibly with some extra expressiveness of a CAS, you have a huge upshot, right? The upshot is you don't have to write special purpose search code, which I know from experience is difficult to write, even harder to make efficient, and almost impossible to verify, right? Where if you use the SAT solver to do your searches, the encoding is much easier to write. It's much easier to make it efficient because SAT solvers are already very efficient, right? There's decades of work that's gone into making them efficient. And you get the verification also because it gives you the certificate at the end. So I want to mention as future work, we're excited to apply this to new applications and see how far we can push it. It's still kind of a novel paradigm. You know, only the last couple of years we've really been using it. I'm starting as an assistant professor next month. So of course, I'll be happy to looking for new collaborators and students and see how far we can push this. So if you are interested, my contact info is at the bottom. So get in touch, and I'd be appreciative if you know someone, you know, if let anyone who might be interested know, and I'd be happy to take any questions right now. So thank you so much.
Thank you, Curtis.